research project and you wanted to find the merger history of a galaxy, what of our three components would you look in? Where would you look? When you think you have an answer, throw it in the chat. So stellar streams, halo. Yeah. Perfect. So stellar streams we saw were going to be found in the halo with all the other older stars, and then also the coronal gas and the dark matter. So yes, you would look in the halo, just as a quick review for that. A+. Okay. So shifting into, that was just a tiny bit of review. Now we're going to shift into what we actually are talking about today, which is our PDRs, our HII regions, and our GMCs. So these are going to be things, for the most part, again, we're focusing on spirals because that's where the stuff is found. There's not going to be as much going on in the ellipticals because there's not gas and dust so much for this to happen. But this is just kind of a snapshot of what we're looking at. The H2 region is going to be the region around a young star cluster. So this is going to be the H2 region. The PDR, it's not labeled here. We will talk about the PDR, the photo disassociation region, is going to be this H1 shell surrounding the H2 region. And then the H2 region is going to form out of a giant molecular cloud, or a GMC. So when a giant molecular cloud, a cloud of gas and dust, passes through some sort of density wave, so maybe goes through a spiral arm, you'll pass it through some sort of shock wave or something, you might get collapse to form young stars. As those young stars form, they will change the environment surrounding them, creating an H2 region and a PDR within your giant molecular cloud. So these are kind of the smaller structures within galaxies. Most of them can be defined by either an H2 region, a PDR, or a giant molecular cloud. Before I go any further, though, I wanted to pause and just have a quick kind of reminder. There are 3 different ways we might say H2, and they all mean different things. So there's H2, H2, and H2. What do those different mean? What do those different versions of H2 actually mean? If anyone remembers one and wants to unmute themselves and shout out.
H2 with it in the subscript means 2 hydrogens bonded together in neutral hydrogen.
Yep. So H2 is molecular, so H subscript 2 is molecular hydrogen, 2 hydrogens bonded together. I will almost always call that molecular hydrogen. Right. Ethan, go for it.
H2 with the superscript is denoting the amount of nucleons it has. So it would be a proton and a neutron.
Yep, so H superscript 2 is deuterium, usually represented by a D, but occasionally as H2, so 1 proton, 1 neutron. So we have one more, H Roman numeral 2, which is what we're interested in.
Like singly ionized hydrogen, right?
Perfect, thanks Thomas. So H Roman numeral 2, which I will actually call H2. So if I say H2 at any time in the semester, I mean singly ionized hydrogen. Because of chemistry, H Roman numeral 1 would be neutral hydrogen, 2 is singly ionized. Is there such thing as H3? Hydrogen only has 1 electron to lose, so we cannot have doubly ionized hydrogen. You can get doubly ionized other elements though, so if you see C3 or something, that would be doubly ionized carbon, O3 doubly ionized oxygen. We just have to remember that it's a 3, but that means doubly ionized because 1 is no ionization, 1 is neutral. So if I say H2, I will always be referring to singly ionized hydrogen, despite the fact there are multiple H2s. Okay, so an H2 region, as you might expect, is a region where hydrogen is ionized. That's why it's called an H2 region. So there will be some neutral hydrogen, but most hydrogen in an H2 region will be ionized. As I showed earlier, it's going to be the hot gas surrounding young stars. So young stars will ionize the hydrogen surrounding them. Since hydrogen is the most prevalent element in our universe, we kind of define things based on hydrogen, typically. H2 regions will have very high temperatures, so there'll be some of the highest temperatures in galaxies outside of the coronal gas in the halo, with temperatures ranging from 5,000 to 10,000 Kelvin. They also have slightly lower densities than some other places. So when I say density, I'm almost always going to be referring to a number density, so a particles per area. So 10 to 10 to the 5 particles per centimeter cubed. As winds from newly formed stars clear out the gas, also supernovas will clear things out slightly as well. So they'll be slightly less dense than the GMCs that surround them. H2 regions are mostly filled with protons and electrons, i.e. ionized hydrogen. So there will be some other gases, some carbon, some oxygen, some nitrogen, but for the most part, our universe is made up of hydrogen with a little bit of helium, so most of the gas in an H2 region will be hydrogen. All of that will be ionized, so it will be mostly protons and electrons. We can use this to define the radius of an H2 region. And this is also sometimes called, the radius of an H2 region is often called the Stromgren radius. And it's just the radius at which we will no longer have most of our hydrogen ionized. So the equation for the Stromgren radius is shown here, where Rs is our Stromgren radius, and then LYC is the number of Lyman continuum photons. So that just means the number of photons that have an energy that can ionize hydrogen. Then in the denominator, 4 pi n squared, n is our density, and then beta here is a recombination rate coefficient. So we're gonna pause, and this is gonna be one of the few times I derive something in this class. So hopefully this will be semi-visible. I'm going to try to work on this whiteboard. So if you can see that, you can try to change maybe. It's going to be hard in the recording. That's where it's going to be tricky. So we're going to start by just defining our H2 region and our Stromgren radius. So our H2 region, we're surrounding our young stars. Our Stromgren radius is going to be the radius at which the number of recombinations is equal to the number of photoionizations. So photoionizations of hydrogen are balanced by recombination of protons and electrons to form neutral hydrogen. So we're starting just by defining this. We're going to make it a nice sphere because that makes things easier. And we're going to say that everything inside our all of the hydrogen inside of our H2 region is going to be ionized. So our ionization fraction, X, is going to be equal to 1. It's just an ionization fraction. And the number of electrons will be equal to the number of protons. That means I'm assuming, again, that the only thing inside of my Stromgren radius is hydrogen in terms of gas, which is a pretty okay assumption, because most of what's inside of this is going to be hydrogen. So there will be, like I said, there will be some helium, there will be carbon, nitrogen, oxygen, but it will be mostly hydrogen. So saying Ne is equal to Np, number density of electrons is equal to the number density of protons, is pretty okay, because every time we ionize a hydrogen, we get 1 electron and 1 proton. So this is kind of our definition. I'm also going to point out that this is a whiteboard designed for Nathaniel. I am closer in height to Andrea. So I can only reach so high. So we're gonna do our best, but I might have to pause and erase on occasion. So we're gonna define our strong gradient radius, like I said, at a radius where our recombination rate is equal to our ionization rate. So we just need to figure out how to rewrite these two values so we can get an R involved. The first thing we're gonna focus on is our recombination rate. We can write the recombination rate as the number density of electrons times the number density of protons. So we need both of these things to combine to get a new hydrogen, a recombination to a hydrogen. So if there's more electrons, more recombinations, more protons, more recombinations. So this is, can kind of make sense. Then there's going to be a value here called alpha, which is going to be a function of T. And alpha is going to be the recombination rate coefficient. So just how likely are we, if we have this density of electrons and protons, how likely is it that two of them will slam together and form a hydrogen? So it's dependent on T because we're going to kind of also assume that we're in thermal equilibrium, so all of our particles are moving with a Maxwell-Boltzmann velocity distribution. So things have kind of settled in, and if you're moving too fast, it's hard to get things to slam together and stick. If it's too slow, it's just unlikely things are going to collide. So alpha is going to be dependent on T. But we're also going to say that alpha in H2 regions, alpha is mostly approximately going to be 3 times 10 to the negative 13th. Somewhere, centimeters cubed, seconds to the negative 1. Okay, centimeters cubed per second. So recombination rate coefficient, it has to be a rate, so it's per second, and then it's per volume because we're thinking of we're thinking in density space.
Will you repeat the value of alpha real quick, please?
Yes. Sorry, 3 times 10 to the negative 13th centimeters cubed per second. And that's approximate, but it gets used pretty often when people are modeling the ISM or H2 regions. Okay. So we're getting close. There's just one more step we're going to do here before we move on to our ionization rate. We're going to say Ne is equal to Np, so we're just going to rewrite this as our recombination rate is equal to Ne squared alpha as a function of T. So this is as a function of T, not multiplied by T. So that's our recombination rate. Now we can think about our ionization rate. I think exactly how I want to do this. Sorry. We have Ni is going to be equal to, where things get a little confusing. I might call this variables. Sigma. Sometimes this is called alpha, and I don't want two alphas, so that's why I'm getting annoyed at myself. Okay, N, H, J. So here we have our ionization rate is going to be equal to the sigma here is going to be the cross section of neutral hydrogen. So that's essentially the size of a neutral hydrogen. The number density of neutral hydrogen, and then the number of ionizing photons per area per second. So this is going to be the rate of kind of a flux of ionizing photons. So this is like, how likely are we that our ionizing flux is going to hit a hydrogen and ionize it? So size of a hydrogen, amount of volume in our area that is hydrogens times a flux per area that could ionize hydrogen. Using the inverse square law, we can rewrite this. This is where I'm as the number of Lyman continuum photons divided by the volume. So we're just going to rewrite this. This is the flux, the number of Lyman continuum photons from our star. So that's just a number, not a flux. Just the number of Lyman continuum photons from our star divided by the volume of volume surrounding that star at a radius of r. So those Lyman continuum photons fill that volume. We can just rewrite this value using as the number of Lyman continuum photons divided by the volume of a sphere surrounding those stars, putting out the Lyman continuum photons.
I don't know if anyone else is having this problem, but I can't really read it at all. So I was wondering if you could put pictures, like take pictures of it and then put it online.
Absolutely, yeah.
Perfect, thank you.
Sorry about that. I tried moving closer. I wonder the other thing I can try, at least for this last step. I'm not sure how well I'm going to be able to do this. Let's try this. We're going to try this. So I'm just going to skip to the last step. So we have our Strongin sphere. We want n r equal n I. And we know, you said n r equals sorry, this is more difficult than it should be, or I just suck, one of the two. And n I is equal to okay. So that's pretty, I hope it's kind of what I just walked through, but you couldn't read. So we have our recombination rate, which is the things we are recombining times the recombination rate coefficient, and then our ionization rate, which is equal to the number of photons that can ionize hydrogen divided by the volume with which we are looking in, so 4/3 pi r cubed. So I just moved my 4/3, I turned it into 3/4. So we're dividing. So we want n, so let me undo that. So we want these two things to be equal, and we want to solve for r, because that's going to be where, so setting these two things equal will turn this little r that looks like a v, but is an r, into our rs, our Strongin radius. So when n e squared alpha function of t equals 3 n And I'll also finish this and post a picture of it so it'll be prettier. But now we can turn this little r into capital R sub s and solve for that to get r s equal to 3 n Lyman continuum over 4 pi n to the 1/3. Okay, that kind of looks like a 3. So that is my quick derivation of the Stromgren radius. But what we can see really quickly, just to kind of plug some numbers in, if we have two O3 stars in our H2 region, then using a chart I showed a little while ago that I will share as well, sorry, I showed 2 classes ago, I think, we can say each O3 star has a Lyman continuum, puts out 10 to the 50th Lyman continuum photons per second. So our n, if we have 2 O3 stars, n Lyman continuum equals 2 times 10 to 50. So yeah, and this is just a number, you would just look this up. This is something I will always give you. It's not something that I calculated in any special way. We have our alpha, we're gonna say is equal to 3 times 10 to the -13th. I don't want to write my units because I'm being lazy, but that should be centimeters cubed per second. Since we are in an H2 region, we can assume alpha is this and be okay. And we're going to assume an electron number density of 100 for now, because that is, our H2 regions could be 10 to a couple hundred. So this is pretty typical for an H2 region. Plugging all that in, you should get, I did this earlier, RS, our Stromgren radius of 2.52 times 10 to the 19th centimeters. So you guys can check me. I encourage you if you want to test this out. That's all the numbers you should need are in here. Or you can convert that to something that makes a little more sense. That is about 8.2 parsecs. So if we had an H2 region with only 2 O3 stars in it, we would have a Stromgren radius of about 8.2 parsecs. So not huge. These aren't giant structures. They're fairly small, but that we would also likely have more than 2 O3 stars inside of you. There would also likely be some B stars and some other O stars. So that's our little dose of derivation. Any questions before I move on? Sorry, viewing is tricky. I'm going to go back to sharing my PowerPoint and not do any more derivations. Okay. So that was a little math. Now I'm going to kind of switch we know how big H2 regions are. I wanted to spend a little bit of time talking about what a life looks like for an electron inside of an H2 region. So these are kind of four main steps that might happen if you are an electron inside of an H2 region. First thing that's going to happen is you're going to be in a hydrogen. You're going to be hit by a photon with at least an energy of 13.6 electron volts, and you will be ionized. So you will fly off into your H2 region. You are free. You are no longer part of the hydrogen. The energy of the electron is going to have the difference between whatever your, should be new, but I was lazy. So the difference between the emitted light that hit the hydrogen and the light that is emitted after. So the light that gets released is going to have lower energy, longer wavelength, shorter frequency. Always have to pause and make sure I say that right. And this will give us also the kinetic energy of the gas. As you fly off from your hydrogen, there's a good chance you will bump into other electrons, and over time, our H2 region will become thermalized, which just means that we have established a Maxwell-Boltzmann velocity distribution. So that curve that you should look semi-familiar, we'll get to a point where our velocities of our electrons, we have this nice Maxwell speed distribution as they bump into each other and exchange energy through collisions. Now, at some point, there are other things inside of our H2 region. There are other ions like singly ionized oxygen. So there's a possibility that eventually you as an electron will bump into a singly ionized oxygen and lose some of your energy as you bump that oxygen into a slightly higher energy state, and then it radiates it down. So there's a few different ways. We will talk about this more when we talk about cooling in the ISM, but like the oxygen 63 micron line, neutral oxygen 63 micron line is a cooling line where electrons bump into oxygen and it radiates at 63 microns. It's a spin flip transition, so that's why it's not losing an electron or anything. It's just an energy transition where one of its electrons is changing spin and then falling back down to ground level and radiating away a photon with a lower energy. So the electrons will lose velocity, will cool down sort of as that happens. Once you're cool enough, once you're not moving too fast, it's possible that you will bump into another proton and become hydrogen again, plus some energy that gets radiated away. So these are the basic things that can happen to you when you're an electron in an H2 region. And like I said, we'll talk more about the collisional de-excitation when we talk about cooling, because those are pretty important when we think about the energy balance within galaxies. Since most of everything inside of an H2 region is electrons or protons, these are pretty much the reactions that we see within an H2 region. So this is what's happened, besides stars forming, this is what's happening in the gas of an H2 region, are these four things. Pretty much nothing else is happening. And the protons obviously will be moving around a little bit as well, but since they're heavier, it's harder to get them to thermalization. So we talk about electrons more just because they play a bigger role in what's going on, since they're lighter and it's easier to speed them up and have them bump into things. Any questions on H2 regions before we shift to PDRs? Okay. So PDRs, your reading was kind of focused on PDRs, but they're kind of the most complicated part since they're where a lot of the chemistry happens. PDR stands for, I call them photodisassociation regions. Some people will call them photon-dominated regions. Both are PDR, so I don't know. I don't think it really matters. They mean the same thing. PDRs are going to be the areas surrounding H2 regions where high energy light still dominates the chemical process. But we are outside of an H2 region, so our hydrogen is no longer ionized. Most of our hydrogen will be neutral. We have run out of ionizing photons. All of those got used up inside of the strong grain radius. So we now only have lower, we're still dominated by high energy light, but we're kind of missing the most high energy light. So the anything with an energy, photons with energies greater than 13.6 electron volts won't really exist in PDRs. I threw in one little chemical equation here to show just as an example of what photodisassociation is. So photodisassociation is when a photon bumps into a molecule and breaks it apart. So these would both be examples of photodisassociation. We have water, it gets bumped by a photon, and we end up with hydrogen and OH. Hydrogen monoxide. I don't know, does that have a name? I don't know chemistry. For the most part, we don't have a lot of molecules inside PDRs because things are still hot enough that they'll get broken up pretty quickly. But there is some dust. There are some, we'll talk more about dust in galaxies soon. But there's dust both in the form of grains and in the form of polycyclic aromatic hydrocarbons. So those things can also get photodisassociated inside of a PDR. As I said, within the PDR, we're still dominated by photons, but there won't really be many photons with energies that can ionize hydrogen. So energies greater than 13.6 electron volts, because those all got used up ionizing hydrogen inside of our H2 region. They get absorbed, re-emitted at lower wavelengths, so we don't see any more once you exit the H2 region. Instead, we'll be dominated by far ultraviolet photons, which is just any photon with an electron with an energy, of 6 to 13.6 electron volts. So that's our definition of FUV. Whenever we talk about that, this is what that is, the energies we are interested in. It's like a wavelength, 912 angstroms to 206. You can calculate that. I always forget the lower one, but the upper one is the Lyman break. So it's that 912, and that's a number that 912 angstroms is a number that you should keep in your brain since it's fairly important. Densities in PDRs can vary quite a bit. We are no longer really talking about electron densities usually when we talk about densities in PDRs because there will be fewer free electrons. There are still quite a few, but the density is going to be more neutral hydrogen now. So when we talk about densities in a PDR, we're usually talking about the density of neutral hydrogen. And they can range from 10 to 10 to the 7 depending on where you are within the PDR, so how close you are to the H2 region. Similarly, the temperatures will range from about 10 to 10 to the 3rd Kelvin, with hotter temperatures near the H2 region and cooler temperatures as you move away from the H2 region. Just like ogres, PDRs have layers. We can model PDR layers based on the amount of ionizing photons, the energy of the photons that we expect to be at that layer. So we can think in this schematic, we have our young stars, our O and B stars. Oh, I should know, ISRF. Visual stellar radiation function. I can't remember. I should check that because it's an acronym that gets thrown around a bit. But so we have our H2 region here, and then we reach a point where all of our hydrogen ionizing photons are used up, and hydrogen goes from being ionized to being neutral, and we are no longer in an H2 region, we are in a PDR. So right after that, temperatures will still be pretty hot, and we will have neutral oxygen, because oxygen ionizes at 13.6 electron volts as well. But we will still have singly ionized carbon. Carbon has an ionization potential of 11.3 electron volts. And then we will have neutral hydrogen again. As you move through, we run out of photons with the ability to disassociate H2, so hydrogen wants to be in H2, so eventually we'll hit a place where all of our hydrogen is in H2 instead of atomic hydrogen. Will be in molecular hydrogen. I said I would call it molecular hydrogen, I didn't there, I'm sorry, but so we'll reach a radius, a distance from our young stars where our hydrogen becomes molecular. As you go through further, we'll reach a point where carbon, there's no longer photons with energies of 11.3 electron volts. So carbon goes from being singly ionized to mostly neutral, and then very quickly bonds with neutral hydrogen to form carbon monoxide. As you move out again, sorry, I have to, you guys are blocking my notes. As you move out, we get cooler. So as we transition from the H2 region through the PDR towards the giant molecular cloud, we get lower temperatures, 10 to 100 Kelvin, and we have more molecules and fewer ions. Typically, this isn't measured in a distance, it's measured in an absorption. So AV is the extinction at the V band in magnitudes. So because these distances depend on how many young stars are here, the size of your H2 region essentially, we never see this plotted as a function of distance. Instead, we always see it plotted as a function of extinction. So this is just AV of 1, we have an extinction of 1 magnitude. AV of 10, we have an extinction of 10 magnitudes. So this is something you've probably seen before when we look at our distance modulus. Sometimes you will add an extinction to take into account dust in our galaxy or dust in the galaxy it comes from, whatever you're looking at, depending on where you're looking. Just in case that wasn't confusing enough, here is a slightly more complicated diagram showing essentially the same thing, but in a slightly more complicated way. So this is our, again, as a function of extinction, different, just kind of how much we would expect to have of different ions and molecules. So you can look at, for example, if you look at ionized carbon, we have this line here where inside, closer to the H2 region where we have low AV, most of our light from our young stars hasn't been absorbed. Pretty much all of our carbon is in singly ionized carbon. When we hit an extinction of 4, all of a sudden that plummets and we end up very briefly with most of our carbon in neutral, but then really quickly that becomes carbon monoxide. So this is just, you see graphs of this that plot models of PDRs showing which ions you would expect to find where, which molecules you would expect to find where. And we can use these kind of models to predict different properties of our PDRs, like the density and the temperatures of the PDRs that we measure. So don't worry about trying to copy all this. This is just to show you kind of what these graphs look like and how you might want to read them. Really what we're usually interested in is ratios of these different elements. I wanted to pause here really briefly as we talk about PDR regions to talk about Hamming units. So this is a way that we often measure the FUV radiation field within a PDR. So G0 is just defined as the FUV radiation field. It's always G0, it's never G. So I don't know what the naught means, but it's always G sub naught, G sub 0. And that's just the FUV radiation field inside your PDR. And it's a measurement of the intensity of the starlight. So higher G0s means there are more O and B stars, there's more FUV radiation. So it tells you a bit about what's happening inside of your H2 region and by extension, the PDR. G0 is typically measured in Hamming units, where 1 Hobbying unit is equal to 1.6 times 10 to the negative 3 ergs per second per centimeter cubed. Because of that, G naught is typically unitless, because we divide a flux by a flux, so we lose our units, or we're in Hobbying units. But you don't typically say that. So if you see a G naught and it doesn't have a unit afterwards, it means it was divided by this 1 Hobbying unit value. We're typically interested not so much in G naught alone, but really in this quantity G naught divided by N, G naught divided by density, because that tells us how much energy there is per hydrogen atom in a PDR. So that tells us a lot about the temperature in this PDR, how often are we getting collisions or atoms colliding, just what are the physical conditions inside of a PDR. And if we know that, if we can model that, then we can get a lot of other information about a PDR. And so this is something I grabbed, this graph here, I grabbed from the PDR toolbox, I think. Sorry, it's either toolbox or toolkit, and I always get it wrong. But it's one of the many PDR models out there. There's another one called Cloudy, but they're different things that you can plug in properties of your PDR, either intensities of different lines or fluxes, or this one is using temperature. And you can figure out what your G naught and your N should be based on where your value is. So if we know that our PDR has a surface temperature of 100 Kelvin, we know that G naught and N must fall along this line. So these are just, again, I don't want you to try to sketch this out or anything, just something you should see. This is a PDR model and is something that is often used to determine the conditions within a photodisassociation region. And typically what you're getting out, you're plugging in different values to try to figure out what the most likely G naught and N's are, the FUV radiation field and densities are within your region. So, yep, I think that was most of what I wanted to say about PDRs. Does anyone have any questions before we move on to GMCs? Okay. So giant molecular clouds, GMCs, are the next level, kind of back. We had our initial diagram where we hit our GMC, our cloud of gas, hit some sort of shock front, some sort of density thing to get collapsed to form an H2 region, that ionized stuff, which is surrounded by a PDR as atoms absorb the high energy light from those young stars. But then what that actually started as was a giant molecular cloud. So just a big cloud of molecular gas. They're going to be fairly cool, so cooler than the H2 regions in the PDRs, typically around 10 Kelvin, with densities of around 100 particles per cubic centimeter. They can be pretty big, 20 to 200 parsecs across. So our H2 region that we calculated for the 2O3 stars was about 10 parsecs. So these are going to be bigger. By definition, again, molecular. So most of the hydrogen is in molecular hydrogen. This is where I have to be careful. I have to say this because it's a common misconception. We observe molecular clouds through CO lines, so CO rotational and vibrational transitions, instead of H2, because molecular hydrogen does not have any visible transition lines. This is taken from the paper that I had you guys look into a few classes ago, the star formation rate paper, so I want to make sure I say it right. The primary reason we cannot observe these clouds in molecular hydrogen is not, as often stated, the fact that it lacks a dipole moment, but instead of how low the mass of the molecule is. The effects of the low mass is that the rotational transitions require high temperatures to excite, making the bulk of molecular hydrogen in typical clouds invisible. So usually people say we do not see emission from molecular hydrogen because it's symmetric, because it has no dipole movement. That is not the problem. The problem is that it has a really low mass, which makes it the rotational and vibrational transitions very high energy. So anything that could, any light that could excite those transitions is also high energy enough to break up molecular hydrogen. So we don't see those transitions. Each molecular hydrogen is invisible. So I have to say that because it's something that gets said a lot and it's not quite right. So instead, to measure molecular clouds, we look for CO luminosity, and then we predict the CO gas mass with alpha CO. It's a conversion factor. So we take CO luminosity, we multiply by alpha CO and get a gas mass. Thinking about trying to go outside and said gas mask instead. Okay. So you'll either see alpha CO, sometimes you will also see XCO. That will convert, instead of converting to a gas mass, that'll convert into a number density or a number of molecular hydrogen molecules. So I kind of put an equation here where you have a number of molecular hydrogen molecules is equal to XCO, our conversion factor, times the intensity of a CO transition. There is a huge debate about what this value is. We don't really know. It seems to be different depending on where you look. So that's semi-problematic because we use this equation to get gas masses for galaxies throughout the history of the universe. So if we do not know what XCO is and how it changes as a function of metallicity, dust content, temperature, who knows what else, we are very likely getting our hydrogen, molecular hydrogen gas masses incorrect. So that is a whole field of research that I am not a part of, but you should know that there's a huge debate going on about what this is and how to refine it and better measure it so we can actually get molecular hydrogen gas masses for galaxies, both in the local universe and in the high redshift universe. Last thing, I just threw this image in because I thought it was cool, but this is the LMC in optical light with the locations of the GMCs mapped over as yellow points. So they looked at the LMC in CO, and then whenever things were bright enough, they said there must be a giant molecular cloud at that location, and they put a little contour down at that point. And what we can see is that it's fairly well correlated with where the H2 regions are. So where things are brighter in the optical red, especially optical red, is a sign that there's H alpha light. So there is an H2 region in those areas. Singly ionized hydrogen emits in the radio, so it's hard to see, but we also get a lot of H alpha, especially from the PDR surrounding them. So we can look for those things. We can see that GMCs are fairly well correlated with the reddish H2 regions. There was a thing that said, something weird is happening here because of OMC3, which I think is this guy here. So this might be an artifact of the fact that we have a really, really, really bright spot here. Because CO transitions are longer wavelengths, it's hard to get nice resolution. You're often getting CO maps from ALMA, so millimeter wavelengths, which means our resolution is not going to always be great. So less about GMCs because I know less about them, but I think this is kind of a good summary of what's going on inside of GMCs. Does anyone have any questions there? Okay, so then we're gonna move on to our coding activity. This is, for the most part, I've kind of tried to have the coding activities fit with what we talked about in class. This one doesn't really, but it's something that I want you to practice for your photometry project. This is kind of the last thing you really need to know. I also am going to ask you to do a background subtraction, which I will talk about next week, but that you can do after you've done everything else. So this is I do ask you to smooth. This is a little bit of a confusing step, so I'm going to try to walk through it. So as per usual, in your date assignment called PSF measurement, there will be a notebook as well as some data for you to check out. Within the notebook, we will be smoothing, we will be convolving our data to a lower resolution. So this is something we pretty much always have to do if you're using more than one wavelength of light. And this is because if you are looking at different detectors, different wavelengths, you're going to have different resolutions. We can't take the lower resolutions up to a higher resolution, but we can take the higher resolution down to a lower resolution. You can't extract infinite resolution if you only have blurry. There's no way to do that well. But if we have infinite, we can blur it pretty easily. So that's what we're going to do today with an image of some stars taken in the infrared. So this all should look semi-familiar, just loading some functions, but there's a lot of new ones because there's some mess here. The nice thing is nobody has to use float utils here, so if it's not working for you, there's no two codes, it's all in this one. Then we read in, a catalog that has locations of stars in this image in galactic coordinates. So last class we talked a little bit about L and B coordinates. So this just has those positions of the stars in L and B coordinates. And then also an image. I did a few steps here to make things slightly easier, where I used AstroPi to convert all the pixel values in the image to millijanskis instead of whatever units they were in. Sorry. Oh, I think, yeah, they were in megajanskis per steradian. Sorry, I put it there. 2 millijanskis per pixel. And then there's also a step here that says, if there's a location in this image with a non-numerical value, don't count it. So if there's some sort of flaw in your image and you get either an infinite pixel value, maybe it got hit by a cosmic ray or something else, we don't care about that. So this is just kind of processing of this specific data. It has nothing to do with actual smoothing yet, but just so you can see what that is doing. Sorry. Oops. Then we go ahead and we grab some information from the header, specifically the pixel scale of this image, so how big the pixels are in arc seconds, and the world coordinate system information. We're going to use, this is all stuff I've already written, so don't worry too much, but it's stuff that you can keep in your basket of tricks. We use skychords to convert from galactic coordinates to pixel coordinates. So we put our L and B that we grabbed from our data file that had locations of stars in this image. We're just going to transform that from galactic coordinates to pixel coordinates. And there was these pixels were a little off, so you have to shift them slightly. This is just saying take all those coordinates and add 0.18 to each one in the x direction and add 0.3 to each one in the y direction. So coordinates are slightly off, you shift them slightly. This means that there's something wrong with our WCS coordinates probably, but we can fix it. And then this is just, again, should look semi-familiar, with just one new thing where I have plotted the image, so the star image taken with Spitzer, and I've circled all of the stars from the data file. So I put a little circle, a circle marker at every X, centered at every X and Y position that we grabbed from that data file, and we transformed to pixel locations using our transform code. So far, still we haven't done any PSF smoothing. We've just loaded some data and saw where there are stars inside of this data file. The reason why we need to look for stars is because if everything was perfect and CCDs performed the way we wanted them to, every star would look like a Gaussian. So we can use stars, so the light from the stars would fall off like a Gaussian. So this is kind of what I'm showing here. If we had infinite resolution, the light from a star would fall off as a Gaussian, just based on, it should be a point source because we're never going to resolve a star. They're too far away and they are too small. So the light gets spread out as a nice Gaussian. We don't have infinite resolution. We're working with pixels, so you're going to end up with something that is a little bit choppier. But the shape of this Gaussian, the size of this Gaussian, is going to be the point spread function, or the PSF, for your image. So this is what we are trying to find. We want to find the how spread out is a point source in this image. How much spreading, what is the size of this Gaussian? So to do that, we have to find a star and we have to fit it to a Gaussian. So here I'm just pulling out a little post-it mark, a little postage stamp around the 100th star in my coordinate list. So this is just saying, go into that list of coordinates and pull out the 100th position in the X and the 100th position in the Y. So the 0 tells me I'm looking at the X pixel coordinate, the 1 tells me I'm looking at the Y pixel coordinate, and the 100 is just kind of an arbitrary, I want to look at the 100th star. I then make a little box around that pixel in our data using this code, and I plot it here. So this is just centered on that XY pixel with 30 pixels on either side. So 30 up, 30 down, 30 on either side, because I defined my box size as 30 right there. This is where things start to get messy. If it wasn't messy enough already. It's really just 2 lines, or 4 lines, yeah, 4 lines. These 4 lines are where we fit our data. So we're gonna tell Python we want to use a 2-dimensional Gaussian function to fit our data. So it goes into our package full of models and pulls out a 2-dimensional Gaussian function. And then we're going to say we want to use a Levenberg-Marquardt least squares fitter. So that's the Lev-Mark least squares fitter. So that means it's just a type of line, it's like a type of line fitting, except we're working in 2 dimensions. Understanding exactly what that is not important. Just know that we're fitting using this specific function. Then we can say, use this method for fitting, this least squares model for fitting. So yeah, least squares, like if you think of a line fit, least squares is when you say I want the square of the distance from the line, and that's going to be my ideal fit. So that's kind of the main thing to think about. So use that fitting model, fitting function, and the model of a Gaussian. So we know we want it to look like a Gaussian. To create a model in this XY space that fits our box, this box right here, the data in this box. So X and Y is just an empty box that we're going to put a new model in that will look hopefully like a 2-dimensional Gaussian here. The rest of this is just plotting all of our data, our model, and the difference between them. So I make 3 plots and I say, plot my data, plot this little postage stamp. In the next plot, plot my fit. So F, X, and Y, this is my fit, this is my model. And then in the final box, I plot the difference between them, or the residual. So what I get is I have my data has our star, there's a few other stars around it. The model looks like a point source, this is what we want. And the residual looks like the image minus the model, so the star gets blurred out. The thing that we want to know from all of this is what sigma, what the width of that Gaussian is. And it gets stored as the standard deviation for so the standard deviation of a Gaussian is going to be sigma. So this is just to take the average of the X and Y sigma. So we have a 2-dimensional Gaussian, we want to take the average of the 2 dimensions. So X plus Y divided by 2, or multiplied by 0.5, and then multiply it by the pixel scale to get our sigma in arc seconds instead of in pixels. So this determined sigma in pixels, I want it in arc seconds. So what you will need to do is you will need to do this at least one more time, because we want to make sure that I didn't pull out some magic star that is fit by a magic Gaussian that works really nicely. So you're going to need to find one more star that is also pretty well fit by a Gaussian and find sigma for that. So I just need you to do this step, or this step and this step with a different star. So you're going to be changing this value here to find another star that is well fit by a Gaussian. I did it a couple times. One thing I will show you, not every star in this image is going to be well fit by a Gaussian. So you might have to play around with this value. The 50th star, when I fit it with a Gaussian, I got a nice Gaussian, but subtracting them didn't actually subtract my star. So that means that if my residual, if there's still a lot of data here, then it's probably not a good star to use. When I used a different star, when I used star 125, I was able to subtract my data fairly well and get rid of the star pretty well. So that's kind of what you're trying to do. Once you find another sigma value, you can get an average of those two, and you can use that to smooth. This is the kernel, this is the code, sorry. This is the code to smooth. We want to make a new, our smoothing sigma is going to be the difference between the two, the square root of the difference of the squares. So we're going to smooth to 5 arc seconds. So you're going to figure out what this is by taking what I found in that first one and getting an average with another sigma value. And then you can use AstroPi, makes a kernel, which a smoothing kernel. It just is going to run through and convolve your image, multiply your image by this Gaussian, essentially. So you can say, I want the size of this Gaussian, the standard deviation of this Gaussian that you're going to use to smooth to be equal to sigma. And then we just convolve it. So this is just saying that I used this is just a new set of data that is our data convolved with the kernel using the AstroPi convolve function. So this is just the name of our new data, and then we can plot that, and we can see that it gets blurred, it's nice and fuzzy, which is what we want. So instead of being sharp, we now have a fuzzy image that has a point spread function of 5 arc seconds, so it will match whatever other data that we are working with that had a resolution of 5 arc seconds. So don't have a ton of time left. We have 13 minutes, but I'll go ahead and open up some breakout rooms so you guys can work on this and try to get started. And then when you do find your 1 star, get your average sigma, plug that in instead of my sigma 1 here, and resubmit it with the answers to the questions I ask as well. Before I split you up, does anyone have any questions? I know I ran through a lot, but as with a lot of our code projects, I have given you everything you need. Now it's just kind of replicating what I did with some new values.
So what your sigma 1 is a sigma that you got from specifically like star 100, right? So whatever star that we get will get a sigma out from the code, and then that's what we'll put in on this that you have input 12.
Yes. Yep.
Okay.
Yeah. So it'll be, I guess the one thing, it'll be the average between what you got and what I got, because we want to take an average sigma. So the point of this is to say we can't just use the sigma for one star, because it's very likely we chose a special star or it's possible we chose a special star that has a weird value. So we want to get at least two. Typically, we probably would want to get more like 5 or 6, but for time.
Okay. So we could use like from star 100, and then you also did star 125 that worked well with the Gaussian, right? So we could use like those two and then one that we find.
Yep. I'm only going to require that you get one star that works because a lot of them do not, but try to find one. Okay. So for the last 10 minutes, you guys can work on this, and I will open breakout rooms if you want to work with folks in a breakout room.